Hello everybody. So today we're going to talk about the factors that affect the frequency of a stretched string. To help us with our understanding, we have a picture of a guitar over to the right hand side here, which is of course a stringed instrument. Whenever you play one of the strings, it creates a note of a certain frequency. And then to change the note, what you have to be able to do is change the frequency that string is vibrating at. So we'll have a look at the different factors that affect the frequency of vibration today. So if anybody's ever played a guitar before, they probably know some of the things you can do to change the pitch or the frequency of the string. One of the things that will affect the pitch that the string is playing at and its frequency is by adjusting the tuning pegs here. So these will tighten the strings or loosen the strings. And in doing so, they're going to change the frequency. So we can say that frequency is related to T, the tension in the strings. Another thing that we can say frequency is related to is the length of the string. So for example, if you play a string that's open, then it will vibrate with this fundamental frequency like this. But if you put your finger on one of these frets, say for example the 12th fret here, then what you're doing is you're changing the effective length of that string. So now it can only vibrate between here and here, which is of course a shorter wavelength than if the whole string was vibrating, and therefore a higher frequency. So just showing you that on the diagram again, if you're effectively shortening the string, you're going to have a shorter wavelength, higher frequency wave. So we can say that the frequency is affected by our length. The third way then that we can actually affect the frequency of the string is kind of something that might be able to see here, but certainly anybody who's played a stringed instrument will know that the thicker strings are generally towards this side and the thinner strings are towards this side. So generally as you go from the thicker to the thinner strings, the frequency and the pitch increase. So it's not directly the thickness of the strings, but it's a quantity that we call the mass per unit length, which just means for say a meter of it, how much mass will there be in that in grams or kilograms. So say going from these ones that are all the same length, this one here, the thicker ones, are going to have a greater mass over that length, and then these thinner ones will have a lesser mass. Okay, so just as a reminder there, the mass per unit length is literally just mass divided by length. So we'll have a look now at the formula that actually holds all of these together. So that formula is that the frequency is equal to 1 divided by 2 times the length times by the square root of the tension divided by the mass per unit length. Frequency measured in hertz, length measured in meters, tension measured in newtons because it's a force, and then mass per unit length measured in kilograms per meter. This formula should be kind of intuitive. If we increase the tension or make the string tighter, then the frequency will go up. You can try this with an elastic band at home. If we decrease the length, then the frequency go up. Like we said, if we decrease the length so it's half the original length, then the wavelength will be a lot smaller, so the frequency will be higher. These are inversely proportional. And the mass per unit length is a little bit harder to get your head around maybe, but just if there's less mass per unit length, so basically a thinner string in this guitar example, then you're going to have a higher frequency. So just because the formula is a little bit more complex than we're used to with some of the square roots, I'm going to do it an example here. So I've written out the question. I've actually forgot to put in a question mark. So A string is 2 meters long, it's under 20 newtons of tension, its fundamental frequency is 150 hertz. What is the mass per unit length? So the first thing we'll do, we know that this is a stretch string question, being given a lot of these variables like length, tension, frequency, and mass per unit length. So we're going to write out a formula that ties all those variables together. Frequency is equal to 1 over 2L times the square root of tension over mass per unit length. Now we'll start filling in what we know. So the frequency is 150 hertz. Our length is 2 meters, so 1 over 2 times 2. And the tension is 20 newtons. Our mu then, mass per unit length, is our unknown quantity. Again, we just draw mu, it's like a U with a little tail coming off the side of it. So it's just important here to make sure we are writing out the formula and then submitting it in, because these are both steps that will probably get you marks in an actual exam. So it's really important to be in the habit of it now. If we start filling some of these quantities in, we know that 2 times 2 is 4, we'll leave 150 where it is. This square root of 20 over mu can actually be broken up now. So we can say it's the square root of 20 over the square root of mu. If you've been doing indices and maths, you should be okay with why that is. So now it's up to us how we're going to solve this equation from here. There are a few ways of going through it, so by no means, if my way isn't the way you're going to do it, then that doesn't mean you're wrong, as long as you get out the correct answer at the end. And if this is something you're really struggling with, it's only on the higher level course, so that might inform your decision about whether we want to do higher or ordinary level, but absolutely try and get it anyway. Just so you know, like, it doesn't mean that you're a failure if you can't get it. Maybe you might just be better suited to ordinary, or you might just need more work. What I would do here personally is my first step will be I try to get rid of the quarter, because I don't like fractions. So I'm going to multiply both sides by 4 to do that. So 4 times 150 is going to be 600. And then a quarter times 4 will cancel out. So I'm left with square root of 20 over square root of mu. Now I'll figure out the square root of 20 on my calculator, and it's 4.472. Generally you want to leave as many decimal places as is practical, and then we only round up at the end. But a good rule of thumb is to use at least 3 as you go through all your questions, and then leave 3 at the end. So again, there's a few different ways that we can go about solving this out. One that appeals to me is the fact that I have a fraction on one side, so I'm going to make a fraction on the other side, and then I'll cross multiply. So 600 times the square root of mu is going to be equal to 4.472 times 1, right, which is just 4.472. Now to get mu by itself, we're going to first get rid of the 600. So square root of mu is going to equal to 4.472 divided by 600. Again, we're just dividing both sides by 600 here, which means that the left hand side will cancel out, just giving us the square root of mu, and the right hand side will be 4.472 divided by 600. Now we can use our calculator to try and get that as a decimal. That will give us 7.453 times 10 to the minus 3. And now just to get mu by itself, we need to get rid of that square root sign. So what we're going to do is we're going to square the left hand side and square the right hand side. When we square the left hand side, square root and the square cancel out, so we're just left with mu. On the right hand side, our number works out kind of funny. We get 5.555 by 10 to the power of minus 5. So that's actually just a coincidence there. I didn't plan on that when I came up with the question. But Then our units for mu, we have to think about what mu is. It's mass per unit length. So mass is kilograms, and then length is meters. So kilograms per meter.